What use is an F-call? In a previous discussion I talked about decibels. The take home from that was that a decibel represents a ratio between two things: the gain of an antenna over the gain of a standard reference antenna, or the power loss between the start of a coax cable and its end. I also mentioned that there are several other things with dB in them. Today I'd like to introduce the dBm, or decibel milliwatt. It's a unit used to compare and contrast different levels of output. Unlike the decibel, which is a ratio, the dBm is an absolute unit. It's referenced to a watt. In audio and telephony, it's relative to a 600 ohm impedance, but in our RF patch, it's relative to a 50 ohm impedance. So how do you use it, what does it mean, and why is it useful? Let's look at some large and small numbers. If you look at an FM broadcast radio station, it typically uses 100 kilowatt, a 1 with 5 zeros. If you look at the received signal power of a GPS satellite, you might get 0.2 of a femtowatt, or 0.000 and 12 more zeros, followed by a 2. Using those kinds of numbers side by side is a handful, prone to mistakes, and there are better ways. Instead of using watts, we could also express the output power of an FM station as 80 dBm, and the GPS satellite signal strength as minus 127.5 dBm. Those numbers are much easier to work with. Think of it as 80 dB gain over a milliwatt. When you're dealing with ratios, to string them together, to look at, say, the loss of the output coming out of your radio, through a connector, through the coax, through another connector, into an antenna with a certain gain, using decibels, you can simply add the losses and gains up and get a number at the end that represents the total loss or gain of power leaving your radio and making it into your antenna and being emitted as a radio signal. And why is that useful? Let's say a connector has a 0.04 dB loss at 28 MHz. 20 meters of RG58 has a loss of 1.6 dB. A 10 meter loop antenna has a gain of 2.1 dB over a simple dipole. How would this perform? Well, simply add and subtract. 2.1 dB antenna gain, less 0.04 dB connector loss, less 1.6 dB coax loss, less 0.04 dB connector loss, leaves you with 0.42 dB gain over connecting a dipole directly to your radio. If you have a radio that transmits with 5 watts, it puts out 37 dBm. If you connect it to the system we just invented, the total output of your radio is 37 dBm plus 0.42 dB gain, or 37.42 dBm. The effective radiated output of your radio is now 5.5 watts. If you replace the RG58 with RG8, your antenna system changes from 0.42 dB gain to 1.95 dB gain, just by removing the 1.6 dB loss from the RG58 and replacing it with 0.7 dB loss from the RG8. The radio, again at 5 watts, would effectively radiate 37 dBm plus 1.95 dB gain, making 38.95 dBm, or 7.9 watt ERP. Again, doing maths with loss and gain expressed in dBs and dBms are simple addition and subtraction. If you do this for a 100 watt or a 50 dBm radio, the RG58 based antenna would be 50.42 dBm, or 110 watts, versus 51.95 dBm or 157 watts ERP. Remember, all we're doing is adding and subtracting dB losses and gain to our transmitter output. If that blows your mind, you could now simply add the gains and losses between your radio, the coax, the antenna, the free air path loss, the receiving antenna, their coax and their radio, and actually calculate what an S5 report might mean when you get it for a DX contact. Or you could calculate how much antenna gain you needed for a QRP moon bounce. That's why it's useful. dB and dBm, they're your friends. I'm Onno, Victor Kilo 6, Foxtrot Lima Alpha Bravo.